In episode 1 of this three-part series on my model train elevator control system, you saw the system prototype in action and learned its logic. In episode 2, you learned about the parts and wiring. In this final episode, you will learn how to code the Arduino Uno. Everything we learned in the first 2 episodes has prepared us for coding the Uno. You can follow this procedure to build this model train elevator control system and customize it for your own layout. In this episode, we'll first set up the Arduino Uno for coding. Then we'll actually write the code. If you prefer, you can watch the first part on setting up the Uno to build your own train elevator control system just like mine without having to know how to code. However, if your goal is to customize the control system for your own layout or to learn how to code for other projects, then you'll want to watch the whole episode. To unleash the full power of the Arduino, broaden your knowledge with a myriad of other online learning resources. I'll suggest just 3. For quickie tutorials for model railroaders getting started with Arduino, check out Jimmy at DIY and Digital Railroad. DIY's Arduino Basics playlist includes Introduction to Libraries, basic wiring and coding, and using sensors on your model railroad. When you've mastered those topics, DIY and Digital offers dozens of more advanced Arduino projects to animate your train layout. For Arduino model railroading with a European accent, you can't go wrong with the Fun with Arduino series on Rudy's Hobby channel. I already credited Rudy with helping me to design the logic of my own Arduino system. For a comprehensive online Arduino course, go down under to find this gem from Australia, the Core Electronics Arduino Workshop for Beginners. There's links for all 3 resources in the video description below. Okay, let's get started with setting up the Arduino Uno for coding. Step 1. My Uno microcontroller board is not from Italy but from China, so technically it's an Uno clone, not an Arduino Uno. But my clone works the same because Arduino's designs are open source to encourage innovation. See part 2 of this video series for my introduction to the Arduino Uno. Step 2. Unos are designed to work with other devices, in this case the train elevator control system prototype. Connect the Uno to your personal computer's serial USB port. The Uno's onboard power light tells you when it's getting power. Step 3. Download the free Arduino programming software to your personal computer. A link is in the video description below. The Arduino website has specific instructions for each computer platform. The software is called the IDE, or Integrated Development Environment. Step 4. Download the servo driver library by clicking on a link in the video description below. This webpage is called PCA 9685 Servo Driver Arduino Circuit Diagram and Code. Scroll down to the section entitled Adding the Library to the Arduino IDE and follow the instructions. This free, easy-to-use software enables my microcontroller system prototype to command the 4 train gate servos. Arduino offers step-by-step guidance for the Library Manager tool in the IDE. Step 5. Download my Arduino program zip file from the web to your personal computer. A link is in the video description below. The zip file contains a folder with 3 documents. Double-click on the zip file to unpack it. There's the program file with the .ini extension, and PDFs of the state diagram and wiring diagram. Arduino's term for these programs is sketches. Arduino requires that a sketch file be saved inside a folder with the same name as the sketch. Double-click on the sketch file to automatically open it in the Arduino IDE. Hot tip! Recently I have been getting this message when I open Arduino sketches on my iMac. It didn't seem right, so I did some research. Other Arduino users say it is caused by an unresolved programming bug in the current version of the IDE. Hopefully you won't get this message, but if you do, just click Cancel and ignore it. You do not need to install the command line developer tools. Step 6. In the IDE, pull down the Tools menu and choose Boards, Arduino AVR Boards, Arduino Uno. Then pull down the Tools menu again and choose Port and the serial port connected to your Uno. There's a way to make sure you chose the right port. After choosing a port in the Tools menu, disconnect your Uno from its USB cable and recheck the menu. If your port choice has disappeared from the menu, then you know for sure that you chose the right port the first time. Reconnect the Uno and select the port again. Step 7. In the upper left corner of the sketch window, click on a round right arrow button. This action tells the IDE to compile the sketch and to write it to the Uno's non-volatile memory. The IDE will report the results in a window at the bottom of the screen. If everything's okay, your Uno is up and running the train elevator control system, and you're all done. If there is an error message, try to fix the problem by consulting those Arduino YouTube tutorials I referred you to, and re-click the upload button. If you have questions about this process, post them in the comments below and I'll try to give you solutions. Coming up next, we'll write the sketch code for my train elevator control system. Pretty much all Arduino sketches have three overall sections: variables, void setup, and void loop. There's lots of variables in the elevator control sketch, and they must be declared before doing anything else. Void setup is the next section, where you set the ground rules, so to speak, for how the program runs. And void setup runs only once. The void loop is where the action is. It runs over and over for as long as the Uno is powered up. Fortunately, we already worked out the commands for the void loop. This was the first video of the series, and it looks like this. It's called a state diagram. To download the state diagram, click on the link in the video description below. This was my guide to code the void loop. Before we get into coding, there's two important facts to remember about computers. The Arduino Uno is like a microcomputer. There's an old joke that goes, computers are as dumb as rocks. The joke is actually true because silicon is a rock and computer chips are made of silicon. Well, computers may be dumb as rocks, but they're also very fast and very obedient. The Uno's clock speed is 16 megahertz, or 16 million clock cycles per second. That means that any Uno code runs pretty much instantly, and it'll do whatever you command it to do. The catch is, you have to give the commands in a language it understands. The Uno can't handle even the slightest deviation from its command language, or it won't compile. Luckily, the Arduino IDE makes it easy to correct any errors. With the Uno's speed and obedience in mind, let's now take a look at the elevator control sketch, line by line. The elevator control sketch begins with comment lines to label the sketch. Comment lines start with double-slash characters, and their text is grayed out. This tells the Uno, ignore me, I'm just talking to myself. Using lots of comments makes the code more readable, as does inserting blank lines. The Uno ignores the spaces and reads only the characters. Also, the IDE automatically changes the colors of key terms. So the first line of operational code links the sketch to the servo driver library that we downloaded. Libraries can customize Arduino software for special applications. We included this library for controlling the servo driver board in our sketch to save us from having to write our own code. It's a time saver and lets us tap into the expertise of other users. The next line of our sketch defines a value that must be set for the servo driver board to work. Copy this line of code exactly as it appears here. Next, we declare two variables named gate shut and gate open that set the angles for the servo arms. I experimented with different numbers until I got the angles that I wanted for my train gates. 10 for the gates lowered and 250 for the gates raised. You might want to adjust these values for the angles of your own train gates. Declaring variables right at the top of the program makes it easy to make changes later if needed. Notice that each variable declaration line has 4 parts. Byte means that these are variables of the data type byte, which is an integer from 0 to 255. Arduino requires you to define the data type so that it can set aside an appropriate amount of memory to store the value. A byte variable needs very little memory space. Then comes the variable names gate shut and gate open, which are labels I arbitrarily assign to the variables. I try to use names that describe the jobs that the variables are performing in my sketch. Variable names are case sensitive and must be repeated exactly the same every time. The equals 10 and equals 250 sets the initial number values loaded into the two variables, which will remain constant in this sketch. Finally, according to Arduino rules, each line of code terminates with a semicolon. The only lines in this sketch that do not end in semicolons are the 2 previous lines for the included library. The next line of code is a command that is required for the servo driver board. Copy it exactly as it appears. Next, we declare a batch of 9 variables of data type byte. They have names referring to the peripherals in the control system. The numbers assigned to these variables are the Uno digital pins 2 through 10 that these devices are plugged into. Because we declare these meaningful variable names at the beginning of the sketch, we can use them throughout and don't have to remember which pin is connected to which device. The next 4 variable declarations identify which outputs of the servo driver board the 4 servos are plugged into. Remember that the servo driver board has 16 available outputs, but we're using only outputs 0, 4, 8, and 12. The next 2 variables, state and previous state, do not identify device pins. Instead, they remember the location or state of the train elevator at any given moment. At state 1, the parade level. At state 2, between levels. Or at state 3, the scenic level. The last variable declaration is blink rate, which sets how fast the error LED will blink. The number is in milliseconds. With all of the variables declared with readable names, we're ready to move on to the setup. The void setup section starts with a left curly bracket and extends many lines below to a right curly bracket. Everything in between these 2 brackets is the setup. The setup runs only once. The first 2 commands in the setup initialize the servo library and wake up the servo driver board. Copy them verbatim. The next 4 lines are pin mode statements. They tell the Uno that we're using 4 of its digital pins to receive signals from the microswitches and infrared sensors. Remember from the variable names that these are digital pins 2 through 5 respectively. Input pull-up is the pin mode required for this type of signal. When the signal is high, or 5 volts, it means that the switch or sensor is open, elevator not present, train not present. When the signal is low, or 0 volts, it means that the switch or sensor is closed. Elevator is present, train is present. The next 4 pin mode statements tell the Uno that we're using digital pins 6 through 9 as outputs to the 2 dual relay modules. A low signal, or 0 volts, sent to these pins turns on the relays. A high signal, or 5 volts, sent to these pins turns off the relays. The final 2 pin mode commands are outputs to turn on and off the external and internal LEDs when in error mode. A high signal, or 5 volts, sent to these pins turns on the LEDs, and a low signal, or 0 volts, turns off the LEDs. In the last part of void setup, we set the initial values of numerous output variables so that the Uno knows what to do when starting up. The 4 servo angles are preset to the raised or gate open position. The actuator is turned on, all train track powers are turned off, and the 2 error mode LEDs are turned off as well. That concludes the setup procedure for the elevator control sketch. Now we're ready for action to code the main part, called the void loop. We already have our master plan for coding the void loop. It's the state diagram from the first video in the series. The state diagram tells the story of the train elevator control system in plain language. It starts with a simple direct question: where is the elevator? The answer to this question will be one of only 3 different states. State 1, the parade level. State 2, between levels. Or State 3, the scenic level. We convert the question, where is the elevator, into Arduino code by using the if statement. The parade switch pin is red. If it is low, in other words, if the elevator is present at the parade level, then the command inside the curly brackets is executed. The variable named state is made equal to 1. There are 2 else lines appended to the if statement to handle the other 2 possibilities for the value of the variable named state. In the else if line of code, if the scenic switch pin is low because the elevator is present at the scenic level, then the state variable is made equal to 3, again placed inside curly brackets. But if the elevator is not present at either level, then it must be in between levels, and the else line sets the state variable equal to 2, also inside curly brackets. Notice that running this if statement will force the state variable to be equal to 1 or 2 or 3. No other values are possible. The value of the state variable gives us our answer to the starting question, where is the elevator? Referring back to the state diagram, The value of the state variable determines which branch of code executes, state 1, state 2, or state 3. This branching function is handled by the switch statement. The switch statement responds to the value of the state variable, which was set by the if statement above. The state variable tells the switch statement where the elevator is, so that it can execute the appropriate code or case for that location. The entire code of the switch statement, all three cases, is contained inside curly brackets. Here's the starting curly bracket, and way down here is the ending curly bracket. Now let's scroll back up and look at the case of state 1 with the elevator at the parade level. The state diagram says the first thing we must do in state 1 is check if the value of the variable previous state is equal to 1. If previous state is equal to 1, then exit out of state 1 and go back to the start. Remember that in the setup, the previous state variable was initialized as 0. Therefore, the first time the Uno runs state 1, the answer to is previous state equal to 1 will be no. So the following lines of code in state 1 will be executed. Let's look at the rest of state 1's sequence of events. Raise parade gates, turn on elevator track, turn on parade lead tracks, set the variable previous state equal to 1, and go back to start. The code to perform these steps looks like this. The parade gates are raised with these two commands. This command turns on the elevator track, and this command turns on the parade lead tracks. The variable previous state is set to 1, and the break command sends the Uno back to the start. In these lines of code, the plain language sentences of the state diagram are converted one for one into technical commands of the Arduino programming language. Notice that changing the value of previous state to 1 at the end of state 1's routine means that if the elevator hasn't yet moved from the parade level, the if statement is previous state equal to 1 will be answered yes, and the Uno will exit out of state 1 and revert back to the start, avoiding unnecessary repetitions of the rest of state 1. Whenever the elevator does move from the parade level at the next iteration of the program, the answer to the start question, where is the elevator, will be between levels. So the variable state will be set to the value 2, and the state 2 routine will be executed. State 2 starts by turning off all the tracks. This makes sense because the elevator is moving, and we don't want trains to fall off. The code for turning off all tracks looks like this. Next, in the state 2 routine, we have a very important question. Are any gates blocked? In other words, are there any trains in the way of lowering the train gates? If yes, we don't want to lower the gates because the gates will come down on the trains, breaking the trains or gates or both. To prevent this, the state 2 routine goes into error mode. Everything stops dead in its tracks, so to speak, and waits for the train operator to move the trains out of the way by hand. The state diagram's error mode steps are as follows. Turn on the built-in LED error light. Turn off the actuator, the motor that moves the elevator. And wait for all clear. Here's what the code for these steps looks like. This line of code turns on the built-in LED for error mode. This line turns off the actuator. Simple enough. But the wait for all clear code is more complex. It uses a while statement that we haven't seen before. It means, while trains are blocking the parade level or the scenic level, do these steps. Turn on the error LED. Wait for the blink rate time of 0.2 of a second. Turn off the error LED. Wait 0.2 of a second. And go back to the while statement. As long as any of the 4 train gates is blocked, the Uno will loop through the blink routine. Because the Uno is so fast, the blinking will appear continuous. As soon as the operator removes the blockage, the infrared track sensors will signal all clear, and the Uno will escape the while loop and move on to the next line of code. In the state diagram, wait for all clear loops back to the question, are any gates blocked? When the answer is no, then the Uno will lower all gates, turn on the actuator, turn off the error LED, set the previous state variable to 2, and go back to the start. Here's what the code looks like. We've seen this code for lowering the gates before, likewise for turning on the actuator, and for turning off the built-in LED. The variable previous state is set to 2 with this simple code, and a break command sends the Uno back to the start. All that remains to complete the coding is state 3, which we can go through rapidly because it's just like state 1. Except we raise the scenic gates instead of the parade gates, turn on the elevator track, turn on the scenic lead tracks instead of the parade lead tracks, and set the variable previous state to 3 instead of to 1. With the coding complete, we can target the Uno as shown before, compile and upload the code as shown before, and the sketch is permanently stored in the Uno. As long as power is applied to the Uno, it will repeat the void loop endlessly. Experts claim you can run an Arduino 24/7 forever, but it's probably a good idea to shut it down at the end of a model train operating session and reboot at the start of the next session. That completes this coding tutorial. Before wrapping up this video series, I want to briefly discuss what will be required to convert my control system prototype for permanent installation on my train layout. Instead of the breadboard and jumper wires, I'll install terminal blocks and permanent wires. I'll disconnect the USB and power the Uno with a 9-volt DC power supply. And I'll need to mount the infrared sensors and servo motors next to the lead train tracks. I'll make the mounts for the sensors and servos adjustable for exact positioning. Eventually, I'll gather all these wires into a wiring harness extending from the center of the elevator frame to an electronic shelf along the front edge of the parade level, where the Uno, servo driver board, relays, terminal strip, power supplies, and actuator control module will be mounted. I'll also add a master switch for the whole system. I can't do this work until I have more of the layout built, so I'll go ahead and wire up the parts for now and mount them out of the way. I also must install dropper wires to the elevator train track for DC track power, which will be switched by one of the dual relays. As I get this work done, I'm hoping to post progress videos on this YouTube channel. Add your comments and questions below, and I'll do my best to reply. Thanks for watching to Bethany Branch Line and N Scale.